This video is going to go over constructing a regular pentagon inside of a circle, so inscribing a regular pentagon in a circle by way of using a golden triangle. So before watching this video, you need to make sure that you remember how to deal with constructing a golden triangle. Or you need to have a golden triangle. So we've already constructed a golden triangle, and this was what we've done previously. We had all of our construction steps, and we actually ended up constructing the golden triangle right here of ABL, or triangle ABL, the one coincidentally, not really, highlighted there in bright yellow to indicate it's our golden triangle. And remember, for golden triangle, it was, if we measured it in degrees, 36 degrees up here, and it's supposed to be 72 degrees for both of those two base angles of our isosceles triangle. Okay, so we're going to use this guy when we go and we construct our pentagon inside of a circle. Now remember what we want to do with our pentagon. We need to have it to be constructed inside the circle. So we talked about this earlier. We said, hey, for our pentagon, we need to actually find the 5 points on the circle that are all equally spaced. The first point is arbitrary. It doesn't matter where it is. But the other 4 points, once you find that first point, are going to be equally spaced around the circle. Okay? So what we're going to do is we're actually first going to put in our golden triangle in our circle, and it turns out the location of where the golden triangle is going to live is right here. It's going to end up being one of the vertices of your pentagon, and then the opposite two vertices of your pentagon. So we're going to start off by inscribing our golden triangle in the circle. Bam, bam, bam. And then we'll end up, after we have 3 out of the 5 points of the pentagon on the circle, we'll grab the remaining 2. Okay, so that's where we're going to start. Alright, so I've gone ahead and prepped up a little bit of something for us. I've gone ahead and already pre-drawn the circle here, which is going to be the circle that we put our regular pentagon inside of. So our goal here is we're going to construct a regular pentagon that's inscribed in our circle, and we're going to use our golden triangle, so what we literally just said. I went ahead and put a step 0 here to draw the circle, center O, which we'll assume we already know, because what have we done previously to now? One of your homework questions was, given a circle, you could always find your center. So even if we didn't have the center of the circle to begin with, we could always go ahead and recover it. So we'll assume right now that we've got that center. Okay? And we also said that we've got a radius OA, and we'll go ahead and put that radius in here. We'll do that next. I'll go ahead and also use point A here, which you needed to know in order to get the size of this circle. We'll go ahead and grab that point A as one of our vertices for our regular pentagon as well. So we'll do that in the future. But next, let's go ahead and draw OA. So draw AO. Now, I'm going to go ahead and put in the full diameter. You don't need that. All you actually need is the radius. So up to you whether you want to draw in just the radius or that full diameter. All right. Now, next thing that we want to do is, and I'm going to write this step in a slightly odd sounding way. So what we want to do is we want to copy the angle BAL, which you don't even see in what we have so far, which is because it's not there. So this is the angle BAL from our golden triangle we had previously. So this is going to be the one angle that's not the base angle. This is going to be our 36 degree angle. Okay, so we'll pull that picture over here and show it. Actually, let me go ahead and do that right now. Okay, so that right here, this angle up there, A, that's the one we want to copy. And specifically, we want to copy it at point A right here in our picture. And not just regular old copy it. We want this angle to be centered. Okay. Now, I'm going to go ahead and, even though I'm going to keep that as a step, that's not a step we've ever actually done before, I'm going to write down what that process is. So the first thing that we're going to do to get this centered angle is we're going to bisect the angle A from the golden triangle, that non-base angle from the golden triangle. So perhaps it'll be easier to see if I rotate that golden triangle so it looks upright. Okay, so that top angle right here is the one we're going to copy. So bisect angle BAL. And if you wanted to cite that, that would be Proposition 9 from Book 1 of Euclid. Then we're going to copy the two half angles. So copy the two. And I'm actually going to go ahead and tell you what the degrees are. So those are 18 degrees. Why 18? Because this top angle was supposed to be 36 degrees in a golden triangle. Half of 36 is 18. So these are our 18-degree angles. And specifically, we want to put one on one side of the line AO and the other one on the other side. So on either side of AO. And that's why we had to draw in this radius. Okay. Now if we cite this, this is Proposition 23 from Euclid's first book, and that's proposition just says you can copy any angle to another line, or technically to a ray. And then the last thing we're going to do is once we copy the angle, so we've got this 36-degree angle that's centered on the line AO, in other words 18 degrees on one side, 18 degrees on the other side, we're going to extend those rays of the angle until they hit the circle. So extend the two rays to get points C and D. And as soon as we actually do this construction, you'll see C and D are the points on the circle. And if you want to extend a line, there's a couple different things you can cite. I'm going to go ahead and cite postulate 2. And then once we've done that, I'm not sure why I wrote a 4. Once we've done that, we'll be ready to move on to our next step. For our convenience, I drew our construction of the golden triangle to make it a little bit bigger, because what we're going to do first is we're actually going to bisect this angle up here at A, and then we're going to copy the two resulting angles. Now, I'm going to go ahead and turn this so it's easier to see. So we're looking at the isosceles triangle right here. Now, it doesn't matter how wide you set your compass. I'm just going to open this up to a certain distance. Right about there. You would want to make it wide enough that you're not having to write on top of yourself, but also not so wide that it's difficult to manage. So remember, when bisecting, you do an arbitrary arc. Make sure it intersects both rays of your angle. Then put the pointy end of your compass. You can keep the distance between the legs of the compass the same or change it. It doesn't matter. But at this point, we're going to have two new arcs, and these two arcs, the center of your compass or the pointy end of your compass needs to be at the intersection of the first arc and the rays of the compass. And the radius of these two arcs has to stay the same. So for me, I just drew 3 arcs and I kept the width of the compass the same across all 3 of them. That's because I need to use this same distance set right here on the compass for something in the future, but that wasn't necessary for the actual bisection. Okay. So notice now that we've got the intersection of those 2 arcs right there, we're ready to go ahead and draw in the line. And I on purpose here picked a different color so it's easy to see this bisecting line. So we've got putting my pen here at the point A, lining up those intersections. That looks pretty decent, so draw it in. And we've just bisected our angle. Now, if you look really closely, it looks like I haven't quite made that point A. So that would be, if you're doing it on your own, a little bit of error, and you go back in a pencil, erase it, and get it better, or just draw a second line with your pencil to get it better. I've got pen I can't erase. Okay. Now, once we have this bisection, assuming everything was perfect, we'd have 18 degrees from the orange line right here, the new line we just put in, and AB, same deal on the other side. Okay, so now we're going to use this. Okay, so coming back to where we want to put our regular pentagon. So we've still got this same guy right here, this same angle we've just bisected. Now, at this point, we want to copy that angle. So I'm going to put these 2 guys next to each other so you can see them both. And remember, when you copy an angle, what did you do? First thing you did was an arbitrary arc. Well, we already have this arbitrary arc right here. So I'm going to go ahead and draw an arbitrary arc from point A, and then I'm going to go ahead and make it all the way farther than what I think I need. So I'm going to say, you know what, I know that my 18 degrees on either side of this line AO for sure is going to stay inside the circle. So if I make this new little circle, I made the arc long enough so that it intersected the entirety of the inside of the circle. In other words, it crossed the circle line itself. Okay. Now that we're there, we come back to the original angle in the golden triangle, and here's the key thing. Put your pointy end of the compass on that arc with the same radius as the circle we just drew. Pointy end of the compass on the intersection of that arc and the bisecting line. Okay, technically you could do it on either of these outer two ones as well. I'm going to do it in the inside one. Make sure the shadow from my head doesn't actually intersect here. And then we tighten up our compass and hope that that's tight enough. So I draw a mark. And if you look at that mark right here, you see it doesn't grab the intersection of the arc we were currently on and the edge of the triangle. So that means I'm too far out. Try again, and that looks like we've actually got it. Checking on the other side, and it looks like the intersection actually worked on the other side too, so even though it looked weird up here, we actually, when we made the marks with our compass, hit both of these two lines, so that means we actually were bisected pretty decently. Okay. Then we pull the compass back over to the big picture, the picture we care about now. Here you have to put the pointy end of the compass where AO intersects that circle, really that arc that we've just drawn. And bam, now we've got two intersection points. At this stage in the game, we no longer need our golden triangle, so it's going to go away. So we've now copied our angle, but we haven't quite because we don't have the rays for the angle yet. So we'll go ahead and put in those rays, and we will actually include the second half of 2B and 2C all together. Okay, so drawing in point A to the intersection. And just keep drawing till you get to the circle's boundary right there. Same deal on the other side. We'll line it up with the intersection right here. And point A. And just keep going till you get all the way to the circle. And here's where we'll go ahead and label those intersection points of C and D. Okay. The only reason that looks a little bit off kilter is, well, because it looks like I didn't hit the intersection mark perfectly up here at the top. So we've already got a little bit of error, and you can see that D and C don't look the same distance from where this diameter came through. Okay. Which means our final picture is going to look a little bit off. Okay. Again, I have pen. I'm not going to redo it right now. Okay. So the next thing we'll do is we'll go ahead and draw in the line segment CD. We'll line up the point C. We'll line up the point D. And there's our line CD. Okay. And now notice you can start seeing the error quite a bit right now. And that error is, actually it looks like it's on this side here, that D is a little too far away. It should have been right down here. But if we'd done it perfectly correct, line CD should have been perpendicular to line AO, the extension here. Okay. Now, notice at the end of these three steps, if we hadn't had any drawing errors involved, that should have been an isosceles triangle, specifically a golden triangle, where the line AO, pull it down into the diameter, exactly cut that isosceles triangle in half. Okay. Now, let's move this on to actually get a pentagon, and it turns out there's two different ways that you can get the pentagon. Okay? One of the ways is, if we know CD is an actual side of the pentagon, the shortest way possible is we would copy that chord with our compass. So we grab our compass here, we'd extend it all the way out to get CD, we'd mark then an intersection up here, which would be our fourth point, and we'd mark an intersection on the circle on the other side, and that would be our fifth point. Connect the 5 points together, and bam, you're done. That's the fastest way possible. I'm going to show you Euclid's way. Euclid's way makes it so you can actually prove the construction at the end. Okay, so it takes a little bit more steps, very, very few more steps, but it'll get it so that when you're trying to prove the construction works, it's much easier. So what we're going to do is we're actually going to bisect the angle B and C. Not B and C, C and D. So bisect angle AC. ACD. I'm going to put in the angle ACD there simply because we're going to get some extra lines. And if you read this back in the future, if we just said angle C and angle D, you'd say, once we got the finished picture, okay, which angle C, which angle D. Okay. Now, if we want to bisect these lines, we'll do the same thing that we did when we bisect the lines. I said lines. Bisect the angles. We'll do the same thing what we did when we bisected the angles previously, which is you make an arbitrary mark. And when I say mark, I really meant arc. Technically, an arc's a mark. And then from the intersection of the rays of the angle and that arc, you'll make 2 more arcs with the exact same radius and centers at those 2 intersection points. We'll line this guy up. Point C and that intersection point, and extend this line all the way to the edge of the circle. We're about to do the exact same thing with angle D. So again, doesn't matter the radius, but arbitrary arc centered at D. Make sure you intersect both rays of the angle. Then at those 2 intersection points of the arc and the rays of the angle, you go ahead and make 2 more arcs where these 2 arcs have the same radius. And what I've just done, I just kept the radii of all 3 arcs exactly the same, but you don't have to do that. We'll then go ahead and draw in the line that bisects angle D and extend it so it hits the edge of the circle. B and E then are our resulting points. And at this stage, we are ready to draw in the missing sides. So our missing sides are going to be AB. They're going to be BC. We've got CD. We need DE. And the last one is AE. So point B to A. And then we'll just continue doing that all the way around the circle. So now that we've put in those last remaining sides, we now have a pentagon. Okay? So we've got 5 points, we've got 5 sides. There's absolutely no question in our heads that this is a pentagon. But what we wanted was A, B, C, D, E, that polygon, to actually be a regular pentagon. Now remember what regular meant. Regular meant that all your angles and all of your sides actually were congruent to each other. Okay? Now, let's see why this is the case. If we look at everything that's going on here, we actually need 1 extra line. So let me go ahead and put in the 1 extra line that we need, which is BE. This would be needed in your proof. It's not needed in the actual construction. Notice also you can see how we were off in terms of the construction. This intersection of CE and BD should have actually been on the diameter. So that actually tells you how far off we are in terms of the construction. You should have a single point, not a little tiny little triangle there. So notice that tells you there's a bit of error in this particular construction. Okay. So if we'd done the construction with no errors, notice what would have happened. Okay. We started here at angle A, and the side CD is subtended from a 36-degree angle. We know it's 36 degrees because why? Because we copied a 36-degree angle here. Now, in our case, that's where the error happened because one of my pen slipped when I was drawing the line, so this angle isn't exactly 36. Okay. Now, if we then look over here at angle D from ADE was supposed to be 72 degrees because it was supposed to come from the golden triangle, the guy that's inside right here. So notice when we bisected it, half of 72 degrees is 36 and 36, which means side BC and side AB are both subtending 36-degree angles. Well, if you're subtending a 36-degree angle, this side and this side and this side are all congruent to each other. Now, looking at angle C, same logic applies. Angle ACD was 72 degrees. We bisected it, so we got 36 degrees and 36 degrees. Side ED and AE are then both subtended from 36-degree angles, which means they're congruent to each other. And if we write that out, I'm just going to write it out shorthand here. All 5 of the sides are congruent to each other for the reason we just said, that they're all subtended from 36-degree angles, which is a proposition inside of Book 3 of Euclid. Now, this doesn't give you a regular pentagon. It only gives you a pentagon that's equilateral. So next we have to check the angles. So if we look at the angles, notice what happens here. We have an angle down here at D, the big angle. We know this part's 72 degrees, so 36 and 36. Over here is 36 and 36. And up here is 36. It turns out, notice, that this guy and this guy are what? They're isosceles triangles, which means those 2 angles are exactly congruent to each other. Over here, we have an isosceles triangle again, so these 2 angles are exactly congruent to each other. Same deal here, these 2 angles are congruent to each other. And without going into all the details, because that part of the proof is actually a little bit more complicated, what it turns out to have happened by looking at these long, skinny isosceles triangles right here, what you're able to see is that the angle ACB, the angle ADE, and then the ones up here as well, are all congruent and turn out to all be 36-degree angles. And if each one of those large angles, those obtuse angles from the potentially regular pentagon, is actually built from a sum of 3 angles that are all 36 degrees, well, if you add up 3 angles that are all 36 degrees, you're always going to get that same 3 times 36 degrees sum. Okay, which tells you that the angle A, B, C, D, and E have to then be congruent just because of what you find about those smaller angles that form the larger obtuse angle. And once you get these 2 criteria, the result, of course, is you have a regular pentagon. Notice it was obvious that it was a pentagon inscribed in the circle just by the fact we had 5 points on the circle itself. The key thing here was establishing that it was regular, so all the sides congruent and all the angles congruent.